Hi everyone, I'm Sam Kachuck, a postdoc at the University of Michigan, working on models of calving mechanics and solid earth deformation. Since it's right before dinner now, I'm going to use this time to motivate a series of questions about calving that I've been thinking about, and look forward to discussing them with you before dinner tomorrow. Ice is solid, so it fractures. Ice is fluid, so it flows, and the fractures flow with it, and extend, and join up with other or new fractures. Occasionally, enough fractures coalesce and the ice disconnects, as shown here happening at Pine Island Glacier. How can we represent this small-scale process that can go very fast and depend crucially on minute details of the ice and its history in our large-scale ice sheet simulations? I find that when we try to incorporate macroscopic models of fractures, we end up with catastrophic behavior, or we don't get calving at all. So can we do it? Before we get to that question, a little background. We often represent ice as a continuum, so it's understandable to want a representation of fracture as a continuum process, shown here in traditional volume element form, giving rise to a group of loosely affiliated models under the heading of damage. To focus on just a scalar field variety, we need to imagine the fractures are orientationless, little penny fractures. This allows a handy geometric interpretation of damage as an effective area over which the continuum equations apply. But how to define such a field? Is it the result of an inversion, the factor that allows temperatures, sliding coefficients, and velocities to match up? Is it a density field, representing a continuum of states of ice between intact and broken, taking values between 0 and 1? More macroscopically, can we treat it as the ratio within a volume element of crevasse depth to thickness? Most, if not all of these models link damage to stresses in the ice and environmental conditions, such as basal melting. Now, we might imagine then that how much the ice is damaged affects how it flows. The traditional flow law for damaged ice multiplies the viscosity by the level of undamagedness, the fraction of the gray intact area to the total face area. The implication is that the holes in the ice are filled with stuff that has the density of ice, but is otherwise inviscid. So we could also apply the damage to the hydrostatic balance to fill the voids with water or fern or air. A still other approach is to imagine the damage doesn't affect the rheology until it does, by causing a calving event that transports the failed ice far from our ice of interest. In fact, as we'll see, these aren't the only options, an idea that might offer a way forward. Let's allow damage to evolve without affecting the ice dynamics, taking, for example, an idealized floating ice shelf with the approximate scale and influx as the Amory ice shelf. Our idealization takes the shelf to be a rectangular block within no-slip walls, and the influx from the left and melting from underneath. These white contours show how this scale matches up to the observed grounded margin and terminus. The purple shows the damage, which increases to the front until the ice is fully damaged. Crevasses reach through the entire thickness, as shown in this hatched region. This model captures the approximate extent of the observed ice shelf. But we run into problems when we allow the damage to affect the viscosity of the ice, as we discussed a minute ago. All of a sudden, the ice disintegrates. The stress along the wall causes damage to increase and make the ice inviscid from the outside in, which is not, I think, what we observe at Amory. We're not alone in seeing this. Take, for instance, these figures of the MISMIP Plus experiments from Sun et al. 2017, with another model of damage. Either the floating ice disconnects from the walls, the cyan contours show areas of thin ice, and flows way out, or enhanced damage driven by melt causes the floating ice to disintegrate way back to a retreating grounding line. So we try something else, more discrete calving. When we periodically remove any ice with crevasses that reach through the full thickness, where damage is won, the ice disconnects from the wall and it becomes a tongue again. Would it be okay to consider these two end members of a theoretical coupling function between damage and rheology? The traditional effective stress coupling is a linear viscosity multiplier, shown here, and the calving is like a heaviside function, making ice inviscid and flowing away instantaneously once the damage hits a particular threshold. If so, can we justify any old coupling function that lies in between them, like this one? What happens? I tried this one and we got almost riff-like localized behavior emanating from the wall where the ice starts to thin. Does this indicate the importance of weakened but not absent ice, like a melange? What could this tell us about the history of the front-initiating rifts we observe at Amory? Returning to Pine Island, we observe floating ice shelves, and these provide a crucial control on the rate of grounded ice reaching the ocean. The effect of damage on the ice's rheology, hydrostatic driving stress, its interaction with ocean and atmosphere and subglacial surface, are all potential drivers for ice shelf stability and instability, and I'm looking forward to hearing your thoughts on it tomorrow. Thank you.